let's talk about chi-squared distribution. Now, when you hear chi-squared distribution, I'd like you to think of goodness of fit. So how good is the fit between what we observed and what we expected? Section 3.7 out of the book talks about goodness of fit and specifically about chi-squared distribution. So what is it? Why do we care about it? The chi-squared test determines whether there's a significant difference between what we expected to see in a set of measurements and what we actually observed. So you can see on the right-hand side, this is from the coin toss experiment or activity that we did in class. You can see that we have the Gaussian distribution that is overlaying our histogram of occurrences that we got in class by flipping a coin and counting the number of times we got heads or tails. And so essentially what the chi-squared test is going to help us do is determine, is the assumption that the flip of the coin is represented by a Gaussian distribution, is that a good assumption or not? How good is the fit of a Gaussian distribution for our coin flipped data set? So a chi-squared test can be used to attempt rejection of a null hypothesis, that the data are independent of one another. And so again, like we've talked about with the null hypothesis, is we are going to be using this chi-squared distribution and we're setting up a hypothesis, a null and an alternate hypothesis to determine whether or not the data set is well represented, if the observed data set is close to what we expected to see. And so just like what we've done with other hypothesis testing, we're going to have an experimental value and a border or table value. And so we're going to be comparing essentially the experimental value that we calculate with the table value that we look up from the table of the chi-squared distribution. And so before we get to the table itself, there is this data set of pressure, and it has been rearranged into a data set that allows us to do this normal probability plot over here. So in column A, we have the limits on class intervals, and so we arbitrarily took it to be 0.010 megapascal. So you can see that 0.010, we've put these data points together into these bins of data, and then the next column over is number of times we observed something falling into that data, into that bin. And so between 3.965 and 3.975, we collected the certain number of data points or observations into that bin. And so that's a pretty important concept for this chi-squared, is we put data into bins, and these bins can be somewhat arbitrary. We can come up with them. Sometimes it's based off of the resolution of the instrument that we're using, and sometimes it is something we choose to put them into bins. And we'll talk a little bit about why that's important here in just a minute, because a certain number of data points need to be in each one of these bins. All right, so the next column here is the cumulative number of data points. And so you can see 1 plus 3 is equal to 4. 4 plus 12 is 16. And so you can see we're just adding up the number of data points. So you can see at the end here, we have 100 data points in this set of data. But you can see that we had more occurrences here at the 4.005 megapascal range than we did at the 3.965. So essentially what we're trying to do here is see, is this close to a Gaussian distribution? And you can see just looking at the numbers, maybe it looks pretty good, maybe not. We'll try to determine that using the chi-squared test. Now the D column, all we're doing there is adding it up as well, but we're looking at it as a percent. So number of points as a percent of the total available points. So you can see as we go, we get a pretty big jump in the percentage of points right here in the middle, and then we end up having a smaller jump as we have only one data point going from this bin to this bin. And so if we take this and this column and we make a plot, so we have cumulative percent of data points on the x-axis, and on the y-axis, we have our pressure in megapascals. You can see that we have highlighted here with this blue a pretty good trend that looks quite linear between these points. And we kind of left the data points off of this end and this end because we only had one and they're pretty skewed. But in between this point and up to here, between around 1% of the data and 95% of the data or so, maybe it's a little bit higher than that, maybe it's 97% of the data, somewhere in that range, we've got a pretty good linear trend. Now, it's interesting because in the book we get this figure 3.16 and it shows the effects of data skew and offset based off of this normal probability plot. And so if it is skewed in this way, symmetric, but with too great a proportion of the points distributed at a distance from the mean. But you can see if it's skewed that way, that's what's going on. If it's skewed the other way, it's symmetric, but too great a proportion of the points distributed near the mean. So you can see that it tells us how good is that distribution when compared to a Gaussian distribution based on the shape of this or how linear this is. And so you can see that there's some bounds here showing that it's skewed or non-equal distribution about the mean and what you would see there. So the chi-squared distribution looks like this, and it is kind of offset to the left side, but as we increase our number of degrees of freedom, we get something that looks more and more like a Gaussian distribution. It's still a probability distribution, so the area under the curve is still 1, which is important once we get into the table of data and we understand that we are going to have all probabilities captured under this probability distribution function. So the table looks like this, and you can see that we have variable nu, and then we also have a variable across here, which is our significance, much like the student's t table. And so again, also like the student's t distribution table, we have a line here. We're going to set a specific value, and that's going to be based off of the value coming out of the table. We're going to set that, and we're going to say anything on this side of it, we're going to reject the null hypothesis. Anytime we have our expected value, our experimental value fall on this side of it, we're not going to reject the null hypothesis. And so if our experimental data actually ends up over here, then we will reject the null hypothesis. So we'll run through an example here in just a second to kind of clarify that. But before we do, just like student's t, we've got significance, which is all it's doing is looking on the other side of that boundary that we're putting in. So just like student's t, that's what we're going to use to look up at the data in the table. We have nu, which is also degrees of freedom or total number of variables being compared or number of bins that we have minus our minus our 1, which is degrees of freedom. And that is very important for us to keep track of how many degrees of freedom are removed each time we're doing this. So this is what the table looks like, and we'll look up a value. And again, that value is going to determine or set this bound. And if we end up with our experimental data falling on this side, we're going to reject the null hypothesis. If our experimental data fall on this side, then we cannot reject the null hypothesis. So this is the equation that we're going to use to calculate out our experimental data points. So we've got our observed minus our expected divided by our expected, and our degrees of freedom is k minus 1. So in order to illustrate this, let's look at an example 3.10 out of the book. And what we're doing here is we've got two six-sided dice that are rolled 360 times, and the results are in the table here. And we want to determine if they are a fair set of dice to a 99% confidence. So you can see on the left-hand column, we have the face-up sum, and then on the right-hand column, we have the frequency or number of times we observed that specific event occurring. So we set this up by determining what our hypotheses are going to be. The null hypothesis that we're interested in is the dice are fair. So what we're saying there is the observed is equal to the expected frequency, and therefore this is the distribution is going to be shaped the way we would expect this distribution to be shaped. And the alternate is the dice are not fair. So if we think about two six-sided dice, we are going to have a distribution that looks like this, kind of a pyramid shape. And so if we have this pyramid shape, then we can determine what we expect the frequency to be based on the number of times we roll the dice. Because if it's a perfectly shaped pyramid, then we're going to have, and we have 360 different roles, then we should be able to determine for the face-up sum of 2, we should see that 10 times if it was perfectly shaped. And you can see that we don't have a perfectly shaped because we observed it only 8 times instead of the full 10 times. Same thing with 3, we observed 25 instead of the expected 20. So this is the expected frequency. So you can imagine with different distributions, we would have a different value over here depending on what the distribution that we would expect to see. So in most cases, we're dealing with Gaussian statistics, and so we would expect it to be a Gaussian distribution, and we would use that Gaussian distribution to determine what our expected frequency is for that specific bin that we have selected. So we use this equation here to determine what our experimental value is for the chi-squared variable. And so we do that by looking at the observed minus our expected, and we square that quantity, divide it by the expected. And we do that for each of the bins that we have. So we have bins 2, 3, 4, all the way up to 12. So that means we have a total of 11 bins. And so we do that for each one. We say in that first bin, we observed 8, we expected 10, we divide that by 10, we square the 8 minus 10, and we do that all the way through all of the bins, and we get a value for the experimental chi-squared as 3.358. So we want to keep track of that value because we're going to compare that against what we get out of the table, and that's going to determine whether or not we can accept or reject the null hypothesis. And so we now are going to look up the table value, which is going to set our bound. And so that is going to set the bound right here. And just like in the student's t distribution, we're looking at significance, which is 1 minus our confidence. So we have 1 minus 99 is 0.01, and that is going to give us this column. Now you notice that we don't divide that by 2 here because this is not a symmetric distribution, and so we cannot use the distribution halves like we were before. We can only look at it in one with the complete significance because and so we won't divide this by 2. So that gets us this column, and now our new is our number of bins minus 1 degree of freedom. So we get our degrees of freedom here. So we had 11 bins minus 1, we end up with 10. That gives us this row. And so our value is 23.209, which sets this bound right here. And we're looking to see if our experimental value that we calculated is on the right-hand side or on the left-hand side. But for now, this value, chi-squared of 0.01 significance with a nu of 10 is equal to 23.209. So now we're going to compare those two. I would strongly suggest drawing this figure out every single time, especially if you're going to do it on an exam. Draw this out. It's very clear to indicate that you understand what's happening here. So we're setting this bound based off of the table value. We're saying if it's on this side, or if our experimental is on the right-hand side, we're going to reject the null hypothesis. If it's on the left-hand side, we cannot reject the null hypothesis. And so our experimental is 3.358 that we calculated, and it is very far to the left side, and therefore we cannot reject our null hypothesis. Can we conclude that the dice are fair at the 99% confidence level? The answer is we cannot reject the dice as being fair at 99% confidence. We cannot reject the dice as being fair at 99% confidence. So we cannot reject that null hypothesis. So I made this slide as an aid. It's the 5 steps that I came up with that could help you go through the chi-squared distribution to determine if you have goodness of fit in what you are observing versus what you expected to observe. So the first step is divide the data into bins, and they can be semi-arbitrary. And the reason I say that is because you have to make sure that you have no bins that are unoccupied. All of them have to be occupied. And at least 80% of the bins have to have 5 counts in them or more. And so you can rearrange the bins, or you can combine bins or sets of data to make sure that this is true. And so just keep that in mind, that you can rearrange them. Number 2 is determine the boundaries And generally that is in terms of Z or T values. And so you determine where those bin boundaries are. And then number three is you calculate or determine from the tables the area under the curve between those two bin boundaries. And then you multiply the probability associated with each bin by the total number of occurrences or data points at that observed data set. And then number five is you calculate out the experimental chi-squared value, and you do that by looking at the observed minus the expected, divided by the expected, and compare that with the chi-squared table value that you look up. So a couple of notes here. Bin boundaries are semi-arbitrary. You can pick them as long as you follow the rules from this slide here. I would use a figure to keep track of those bins and just make sure that you don't have some sort of gap that could collect data, or make sure that you do keep track of all of your bins. Be careful of the degrees of freedom. Every detail you choose or statistic derived from a sample population reduces the degree of freedom by one. So picking the number of bins gives us our first -1. So if we pick the sample mean and standard deviation to calculate our expected probabilities, you would have gotten a further two minus, you've gotten a further -2 off of there. So we would have a total of -3 degrees of freedom because we picked the number of bins and we used our mean and we used our standard deviation to calculate the probabilities. And so you could have -3 off of there. And that's pretty important to keep track of. A couple of limitations here. We've already talked about some of these in the steps slide, but experimentally determined values must be numerical counts. That means they have to be integer frequencies. Fractional events don't occur. Also, we have to make sure there's no unoccupied bins. And then the last one is the use of chi-squared is generally questioned if 20% of the values in either the observed or expected cells or bins have a count less than 5. So this is the opposite of that 80% rule. We're just looking at the same rule from a different side. And you can combine them to eliminate this problem. So that is the chi-squared, which is very helpful. And again, when you think of chi-squared, think of goodness of fit. A lot of times we're dealing with data sets that we're trying to say are Gaussian. And so it's important for us to prove if that data set truly is Gaussian, and we can use the chi-squared test to determine if that fit of our expected versus our observed is a good assumption.